Hi everyone, this is Venkata Akiraju and we are from Team Antonia. Today we are going to discuss about advanced surface construction techniques. So we are the members of Team Antonia. This is myself Venkata Akiraju and Sai Srinija, Srinivasan, Anupriya and Prashant. So today we are going to present you some advanced surface construction techniques such as swung surfaces, skinned, swept, Gordon and cone surfaces. Here the basic idea is to take one or two curves or some set of curves and create a NURBS surface which interpolates these curves given the curves are isoparametric curves in the NURBS direction. And we also have some design examples and GM lab demonstration after the construction techniques are discussed. Now let us see in detail about swung surfaces. A swung surface is a generalization of a surface of revolution. It is defined by a profile curve and a trajectory curve. And in the construction of a surface of revolution, the profile curve performs a complete rotation about the axis of revolution. Profile curve rotates about the axis of revolution, but the rotation does not have to be 360 degrees and it's controlled by trajectory curve. Now let us see what it means in detail. To the right, we have figure 1, where the profile curve is defined by the points P0, P1, P2, and up P5, and the trajectory curve is defined by the points T0, T1 up to T10 in the XY plane. Here if we see, the profile curve is in the XZ plane, and the trajectory curve along the XY plane. Now if we rotate the profile curve along the Z axis, if we rotate it in 360 degrees, we are going to get a surface, but we are not going to rotate it in 360 degrees. Like in the previous presentations, we have seen how a curve is rotated around z-axis and that yielded some flower vase or sphere. But here, instead of rotating it in 360 degrees, the path of the rotation is defined by another curve, and that is called the trajectory curve. Here the profile curve and trajectory curve are given by the equations here defined by P of u and T of v, and denoting the non-zero coordinate functions of P of u and T of v by P of x of u, P of z of u, T of x of v and T of y of v. The swung surface is defined by this equation. S of u comma v equal to alpha px of u tx of v comma alpha px of u ty of v and pz of u. Here you may see why there is no coefficient or anything for pz of u, because here we are rotating around the z-axis. We are not changing anything on the z-axis. That is why p of z of u doesn't have any coefficients. Now curve S of u is obtained by swinging p of u about z-axis and also simultaneously scaling according to t of v, where alpha is an arbitrary scaling factor. Now let us see what that means is. So we have points P0 to P5 defined, but we need to rotate them along Z, but that should happen along the path of the trajectory curve. So if we scale the X and Y coordinates of the P points when we rotate it along the Z axis and scale it in such a way that it is traversed to the path of the trajectory. By scaling the X and Y in such a way that it follows the trajectory path, we are going to rotate this profile curve exactly along the direction of the trajectory curve. These equations define the u and v naught vectors for S of u, and q of ij is the new control points that are defined when we rotate profile curve along the trajectory curve. Now let us see this example. For the figure we have seen in figure 1, let us see what happens if we are going to swing the profile curve along this trajectory. So this is the control net that is formed, and these are some example weights. And here we choose the scaling factor to be 0.12. So after rotation, this is going to be the control points, and figure B shows how a swung surface is formed when we rotate the profile curve along the trajectory. So here the generated swung surface, it appears to look like a profile curve if you look from the front, like if you look straight towards the z-axis from xy plane, and it looks like the trajectory curve if you look from the z-axis towards the xy plane. Like if you look from top, it appears like a trajectory curve, but if you look from front, it appears like a profile curve. So just to give a more idea on how swinging can look like, so if I define the trajectory as a circle, so the path of the trajectory is a circle defined around the origin, like radius, this center point of the circle being at the origin. And if we have a profile curve that is like a S based curve, and now if I rotate it along the circle, I'm going to get something like a pot shaped curve. Here the trajectory is a circle. Now let us see one practical example here, where profile curve is defined by S based curve towards the left, and the trajectory is a semicircle. And if we swing it along the semicircular trajectory, we are going to get a bell shaped, a half bell to the right, and the wireframe is shown on the rightmost, where you can see the new control points. Now let us see what are skin surfaces. A skin surface is a surface that contains a set of curves C1, C2, Cu, and these curves describe the shape of the desired surface, and they are called section curves. In practice, they are usually planar cross sections in the U direction of the surface to be constructed. So in skinning, we have some base curves, they are called section curves. So imagine it this way, like we have some curves defined, and if you put a sheet or a skin on top of these curves, it appears as if we covered them with skin, and the resulting surface appears as if a skin has been placed or covered the skeleton. So that is why the name skinning comes from. So here the section curves, like you see in the figure 3a, C0, C1, they are defined along the u-axis. They are the basis, and after interpolating these curves, we get a surface that appears like a skin has been formed around them, and that is the resulting skinned surface generated by interpolating these section curves. And these section curves are planar cross sections, and the interpolation happens in the v direction. So here the k is the number of curves. We can have 0 to k curves. And historically, skinning has been used in shipbuilding and automobile designs. Now, before we dive deep into skin surfaces, I just want to give you a visual representation of how skinning looks like. So here is the example where it has some curves. If you see, it appears as if I placed a sheet and covered them, and this is the resulting surface formed, but it is not formed by placing another curve. We are actually generating this by interpolating these section curves. So this is the idea behind skinning. Now let us see the mathematical foundation and other concepts that are used for skinning. So let the section surfaces be defined by this formula. Sorry, the section curves defined by this formula: Ck of W or U equal to sigma equal to 0 to n of Ip or U, P of I comma K of W, K equal to 0 to K. So these are K section curves, and assuming they have different degrees and different control points. But to interpolate them, we need to have some common knot vector, and we may also have to raise the degree. Then we can do the interpolation smoothly and generate a surface that is smooth. So initially, this is the example we have seen in the figure 3, where the curve, the curve 0, it's a linear. We have only 2 points, and the others are quadrilateral or cubic, and they have different set of control points. But for us to interpolate, we have to bring them to a common knot. We have to define them on a common knot vector, and we may also have to raise the degree of some of these section curves so they are all uniform, and then we can do the interpolation. So if we see, we have the section parameters vk bar, k equal to 0 to k, and a knot vector v that needs to be computed. And then we do n plus 1 curve interpolations across the control points on the section curves. And as a result of this process, we get new set of control points, q of ij, or the skin surface. Now, what are n plus 1 interpolations? So we have seen there are some control points for each curve, but we also discussed we have to define them in a common knot vector. So at the end, as a result of this, we get n control points on each section curve. So we have to do 0 to n or n plus 1 interpolations. So first we take 0th point and then interpolate them across all the curves, like curve 0, 1, 2, 3, 4. Then take 2, so on up to n. So we have n plus 1 interpolations in the v direction for all the k curves. That is why we have this I of j. I is from 0 to n and j is from 0 to k. Now let us see this with some example. It's the same examples, but now we are getting more detailed on what their control points and degrees are and how the resulting interpolation looks like. So here are the curves defined: C0, C1, C2, C3, C4 and their respective degrees. But defining them on a common knot vector, we get 22 control points by combining all these knot points. So and if we do the interpolation, this is the control net we are going to get as a result of this interpolation, and this is finally the skin surface that is generated. So if you look, it appears as if we just placed some sheet on this and we generated a smooth surface that appears as if it is the skin formed on top of the skeleton. Now, there is another way we can do skinning, that is by driving the direction of the interpolation using a guide or a spine curve. So if you see here, we have 5 section curves. Now, instead of interpolating them, we choose to interpolate them using another curve that acts as a guide or the direction for the interpolation. So we are going to join these section curves to the spine at any arbitrary points to get the desired surface, and this spine is going to drive the interpolation. So if you look at, right, this is the actual combination of the spine and section curves that we are going to use for interpolation and generation of a skin surface. Now, let us define the spine curve Cs of V along V bar of K. V bar of K are the points where the section curves intersect the spine curve. And we also take the derivative of the spine curves at these intersection points. We have seen in the previous sections on global interpolation presented by other teams, like how we calculate derivatives in the process of global interpolation and how we calculate the parameters while we interpolate multiple curves. So we are using the same thing here. So we have the spine curve, and we are taking the derivatives. These derivatives define the direction, because these derivative means it is the tangent. So we get the tangent direction and we use that direction to interpolate the direction along other control points. So if you see in the figure 6, we have the derivative calculated d0, d1 at the intersection points. Now for each of those derivatives, now we calculate the derivative value at the other points as a relative length of the derivative at the intersection point. So we get the derivatives at all the control points for each of the curve, and this is the formula used to calculate the derivative at any ith point on the kth curve. So this is nothing but take the derivative value at the intersection point and then as a fraction define that as a fraction or a relative factor using the difference between the current point, the next point, and also the current point to the previous point, and then divided by the distance between the chords. By using the relative fraction of the actual derivative, we calculate the derivatives at each point. So now from figure 6, we can see we got all the direction of the derivatives and we got the section parameters calculated. Now using all these, we can join and then we can interpolate them. So this is the resulting control net we are going to get after we do the computations and get all the linear equations. This is the control net, and figure 7b shows the resulting skinned surface generated as part of this interpolation. There is one more variation, like without having to do any derivatives also we can do the interpolation, but we get a difference, like the direction may not be well defined, and that example is shown in figure 8b where we do the interpolation without taking the derivatives. Now, section curve positioning. Like we said before, we can join the section curve to the spine at any arbitrary point by choosing different points along the spine and also choosing the point where the section curve joins the spine. We get different combinations of skin surface generated. So here are 2 examples that are given. So in the first example, the section curves are placed on the spine as defined by these intervals 0, 0.35, 0.5, 0.62, and 1. And each section curve is intersected to the spine exactly at its midpoint. That is why you have UK cap as 1 by 2 for all the 5 section curves. And now coming to the next one, we have the intervals placed at uniformly like 0, 0.25, 0.5, 0.78 and 1. They're almost like equidistant, not exactly, but very almost equidistant to each other. But if we see the section curves, the first section curve intersects at its midpoint, but the second one at 310, and third one at half, and the fourth one at 910, and last one also at half. So if you see the resulting surface, though they appear similar, but there is difference along the curvature. The surface generated are slightly different. So based on the combinations at which the spine intersects the section, we can have multiple skin surfaces generated. Now let us see some issues if we choose the section curves to be rational. So rational curves, though they yield good results, but there may be several problems. For example, in three-dimensional curves to be smooth and similar shape, but the fourth dimension counterparts may have cusps and totally different shapes. So what this means is if you have a rational curve, the curve individually can be very smooth, but if you have to interpolate two rational curves, that can lead to some unwanted cusp along the interpolation. It leads to some unwanted geometry during the interpolation. That is one problem. And the other problem we may have is during the interpolation, it can lead to some negative weights that can again cause problems like yielding some unwanted geometry. Or if we are using this in any design systems, the downstreams that are going to use these weights for interpolation, they may not do well with negative weights or zero weights. Those designs may fail. That is another problem. So now let us see one example. If you see, we have four rational curves. They look very smooth and they are almost equidistant. So we expect a good skinned surface to be generated. And here are the weights, the control points they're defined on 1, 2, 1, 1, 1, 1, 1, 1, 3, 1, 1, all ones, and 1, 4, 1, 2, 1. But the resulting interpolation is not so smooth. If you see after interpolation, these are the weights we get, where if you see the on 3, 2, the weight is negative. And as a result, we also get a surface like this, which is very spiked at the beginning and the ends of these curves. So we expect a smooth curve to be generated, but we have some unwanted spike. These are some of the problems that we get by skinning using rational section curves. Now, Srinja is going to continue the presentation from here on. Thank you.
Hello everyone, I'm Sai Stranger. I'm going to continue from here on. Let us look at some of the causes of the lofting problems. The first one is parameterization inconsistencies, where we must take care of the parameters such that they flow along the same way and the same direction. The second one is positioning inconsistencies, where the section curves must be placed, otherwise, there can be some wiggles and self intersections. The third one is the continuity inconsistencies, where the curves must be parametric continuous not only in the Euclidean space but also in the homogeneous space. And the fourth one is the weight problems, where we do not want the weights to be negative, so we need to take care that the weight changes are not too large or not too small, but they're moderate enough so that they cannot cause any problems in interpolation and weight scaling. So let us look at few examples. So on the right, we can see the surface formed by the section curves that are taken in the left. So this is another example. This is the surface formed using the section curves on the left. Now let us look at another type of surfaces called swept surfaces. So what are the differences between swept surface and skin surfaces, you ask? So skin surfaces use many section curves and are used for skinning, and they will be skinned together so that they form a surface. In the sweep surface, we'll be using just a trajectory curve and a section curve. So what are we going to do in the sweep surface? We're going to sweep the section curve along this trajectory curve. It can be arbitrary. And the equation or the basic equation that is used all along is this one, where represents the section, the surface, P represents the trajectory, M represents the rotating or the scaling function, C represents the section curve. Now, As the trajectory curve can be arbitrary, there can be some irregularities like self intersections, discontinuities, wiggles, etc. So, to overcome this problem, we can consider two cases. That is, we can consider M of V as an identity matrix, or we do not consider M as an identity matrix and come up with another solution. So, let us look at the example first. So, what is a trajectory curve? It looks something like this. It is arbitrary. We don't know what it is. And this is a section curve which must be taken care of. And when we sweep the section curve along this trajectory curve, the swept surface formed will be something like this. So now let us look at the first case where we consider M as the identity matrix. This case is known as generalized translational sweep. This is because if the M is taken as an identity matrix, then the equation becomes this, which means surface is formed by translating the trajectory curve with the section curve. Nothing of rotation or scaling is done here. So that is the reason why it is called as the translational sweep. So now if we take an example and consider the example of a cylinder, these are the equations that are used, which can be found in the previous topics, that is, in the previous presentations. So these equations are taken together and they are replaced in the equation given above. So this is the swept surface that will be formed for the cylinder if we use the first case, that is translational sweep. Now let us look at the second case. Here we are going to come up with another solution. So for this solution, we are going to consider two coordinate systems. First one is the global and second one is the local. So in the global coordinate system, we are going to consider four coordinates, and in the local coordinate system we're going to consider four coordinates but along each and every vector value. So here we are introducing a new term, that is b, which is a vector valued function which satisfies this equation. So how are the local coordinates represented? They are defined as follows. O of v is just a trajectory curve. X of v is the magnitude of the first differentiation of the trajectory by the magnitude of the first differentiation, and z is the vector valued function b by its magnitude, and y is nothing but a product of z and x. So using these four local coordinates, we are going to define the swept surface as follows. S of u is equal to T of v plus, in the place of the M matrix, that is the rotating function, we're going to replace it with A into S into C of u. So looking at this, we can say that the entire surface depends on A of v and S of v. S of v does not cause any problems, but A of v does, as it is not representable in the knobs form. To make it representable in the knobs form, we have three solutions. The first one is interpolation or approximation. As we know that in interpolation, we need a curve and we are going to use it for the entire process. But here in the swept surface, none of the curves are precise. We are so unsure. So this method is not reliable. So the next one is approximating the curve using of the trajectory using these two cases. That is, we consider T of V as an isoparametric curve only if the section curve passes through the origin. Otherwise, it is not taken as an isoparametric curve. And the third and the most reliable solution is skimming, where we take the instances of the section curve along T of V and then skin them from the beginning. So this is the most reliable one, so we are going to discuss in detail about this in the next slides. So there are two further strategies in skimming. First one is to make use of the trajectory to get the parametric values and the fitting weights. In the second strategy, we are not using T, that is the trajectory. So this is the algorithm that is used for the first strategy, that is using T. So here we are going to interpolate the trajectory. So what are the inputs here? The input is t, c, that is section curve, b is the vector value, and k is the minimum of instances that are required for refining the knot. So first we are going to refine t is not vector, and then we are going to use t to get the control points, and then we're going to find out all the coordinate values. In the second strategy, we are going to use a T of B only for the positioning of the section curve, but for not for anything else. So this is the algorithm here. The trajectory is not interpolated. That is, we do not refine the knot here. We just use the control points to calculate the coordinates. So this is the example. So this is the trajectory curve which is arbitrary. This is a section curve which is not passing through the origin. So if we sweep the a trajectory curve with the sectional curve, then it looks something like this and this. So what is the difference between these two? This is formed using the first strategy, that is by taking or by using interpolation on the trajectory. This is without using interpolation. And let us look at other examples where the section curve is passing through the origin. If the section curve is passing through the origin, then we take it as an isoparametric curve. So for this purpose, we can use the scaling function, and for this purpose, we can use some control points and knots and design the surface as we want. So this is without scaling, but if we use the scaling, then it will be something like this. So the difference can be found here and here because of the control points that we have taken and the knots that we have considered. So this is using these two examples. And next, let us look at how the surface will be formed when a three-dimensional trajectory curve is used. That is, in the previous examples, we have used planar trajectory curve. So this is the trajectory curve. This is the cross-sectional curve that is passing through the origin. So this is when the trajectory is not interpolated. That is the second strategy. This is when the trajectory is interpolated. That is using the first strategy. So these are the examples for the three-dimensional trajectory curves. So as everything is nice and well, we do have some problems with the swept surfaces. First one is it is highly dependent on the position of the section curve, size of the section curve, and also the shape of the trajectory curve. So the trajectory curve is chosen according to the surface that we want to form. So it cannot be changed. So it causes a problem here. So here we have come up with the solutions, that is using interpolation and not using interpolation. In both the cases, there is a problem. That is, there will be some wiggles and self intersections. So these two phenomena is called as offsetting phenomena. To overcome this offsetting phenomena, there is another solution. So let us look at those solutions later, but let us cover another topic. So in the previous slides, I have explained that we are going to introduce a new term, that is a vector valued function b. So how are we going to compute that vector valued function? There are two solutions. The first one is taking it as a constant function, but it becomes a disadvantage for the arbitrary trajectory curves. So another solution is to use the freenet frame. So this freenet frame uh, defines the vector value functions as below, this one. So as you can see, the denominator can cause an issue. So if we use the freenet frame, then there will be unwanted rotation. We can see how. So in the denominator, that is t double dash v cross t dash v, it can become 0. So those points are called inflection points. At those inflection points, b is not defined, and it flips abruptly and it can rotate excessively. So here we can see the third case where it rotates excessively around T, causing unwanted twisting. So to overcome this problem and the offsetting phenomena, a method called projection normal method is used. So this projection normal method uses a sequence of parameter values v0, v1, and so on up to vm, and at each vi, b of v is calculated using these formulae. So in the example, we can see that these points are v0, v1, and so on up to vm, where v0 defines the least value and the vm describes the highest value. So at each point, we are going to consider the vector values, and we are going to change the trajectory accordingly so that there will be no issues with the trajectory curve. This is for the planar trajectory, and this is for the three-dimensional trajectory. So this is all about the swept surfaces and how they can be used in designing various surfaces.
Hi everyone. Today we'll be discussing about Kuhn surfaces. The last thing which has been discussed is Gordon surfaces, and I want to make a point that there is a major difference between these surfaces that the Gordon's method presents a global interpolation to a network of curve, whereas the Kuhn's method more of a constructed a patch within each set of four curves, and hence his was a local interpolation method, and that was the difference between Kuhn's surfaces and Gordon surfaces. So starting on with Kuhn surfaces, these surfaces were named after Stephen Ensign Kuhn, who developed these surfaces in 1967, and but the original idea came from research which was done during World War II in aeronautics. Now, cone surfaces are curved boundary surfaces which are created by filling in an area between multiple surfaces, and these surfaces are mostly used in patching surface geometry errors, which were created by some inaccuracy in plane creation, which finally resulted into holes in the design. So we use these surfaces to remove that accuracy and to get more smoothed surfaces. And this right here is a picture of a cone surface in a three-dimensional plane. Now, coon surface, they are also known by coons patches or simply goes by the name of coons. And these are a type of various parameterization which are used in the field of computer graphics to smoothly join other surfaces together. And if we'll talk about computational mechanics application, they are particularly used in finite element method or boundary element method to mash problem domains into elements. Now, the coon surfaces, these are created using four different curves as input and then interpolating them together using some blending functions. Which you can see right here in this diagram, that these the four input curves which are used, they form the boundary of the coon surface. So this edge1, edge2, edge3, and edge4, these are the boundary of a coon surface, which were actually the input curves which were provided. And though we can use different types of blending functions, which we can use linear functions, bicubic functions, etc. So if we'll take the example of bilinear function, so what we do is what we do the binary interpolation to generate a Kuhn surface. And how do we do it? So what we do is actually we first take a linear interpolation and do it on a pair of a corner. Say if we take this corner and this corner, then we perform linear interpolation over these two corners, and then we take the other remaining two corners and perform the same linear interpolation and generate two different surfaces, and finally we blend them together to get our resulting Kuhn surface. And this equation right here at the bottom, um, yeah, so this equation at the bottom, it shows the equation of a bilinearly blended Kuhn's patch. Moving on. So yeah, now we'll discuss about the Kuhn surface construction. Kuhn surface is constructed by interpolation between boundary curves and blending functions. And just now I told that we can use different kinds of blending functions depending upon our requirements. So these diagrams here at on the right hand side, are they are representing the binary blended Kuhn's patches. And if we'll talk about classical Kuhn surface. So, how do we generate those? So, to construct classical Kuhn surfaces, we use four different curves as the input, which finally forms the boundary of the Kuhn surface. And if we'll talk about generalized Kuhn surface, these surfaces are constructed using four rectangular surface patches as the input instead of the four curves as input. Now, there is one condition which needs to be fulfilled by these curves, which is that all the curves will be in a same parameter domain, where one boundary curve of each forms a side of a curvy linear rectangle. Now, the resulting surface interpolates the boundary curves, and its shape is influenced also by the shapes of the constraint parts. So, what do we mean by this? Is that the resulting Kuhn surface, which we are going to get, um, by interpolating these boundary curves, that the shape of that resulting surface can be changed if we'll shape the if we'll change the shape of the constituent parts. Now, this slide gives an example of a surface, and here we can see how that these were the initial conditions. So this is the bumpy surface, this is cylindrical surface, this is wavy surface, and this is planar surface. So these were the four constituents of the curve, and this is the final resulting generalized cone surface. So what happens is when we change, these are the initial conditions, and in the second picture we can see that the conditions have been changed, the bumpiness has been reduced to almost zero, and then cylindrical surface part has been increased, and the wavy surface has been decreased. Also, the planar is increased. So the conditions changed, and you can see that there is a change in the resulting surface too. Then this is the third example that bumpy surface is increased to its maximum, and these two, cylindrical and wavy, has been reduced significantly. So now we can see how the surface has been changed. Now the next slide will show us a working demo of the same example. This is a YouTube video. So at the top you can see the four different surfaces are getting changed, and similarly how the resulting surface has changed. So when the waviness is decreased, these things just got reduced. And the one thing to notice is that even though the constituent parts are changing and affecting the resulting surface shape, but the boundaries are have remained fixed. Now, we'll talk about the bilinear surface and Kunz patches. Uh, so these surfaces are generated with the same four input curves, but the blending function which will be used here is linear, and the curves which are used here as the input are cubic Bezier splines, which are formed when various Bezier curves are combined together. Now, on the right hand side, we can see the examples of the bilinearly blended cone surface. How do they look? And this here at the bottom, this is a more generalized representation of the same bilinearly blended cone surface. So to explain this, we assume that we have four different points A, B, C, and D. A will be at 0, 0, B will be at 0, 1, C will be at 1, 1, and D will be at 0, 1, and sorry, B will be at 1, 0. Now there are four different input curves: P1, which is between A and B; P2, which is between D and C; Q1, which is between A and D; and Q2 between B and C. These are the four input curves, and these were the four input points. And these are the equations which present these point and the input curves. And the final curve, which is right here, PUV, this represents our final cone surface, which is carried by these four curves. Now, in this slide, you can see that what we do is, since the name is bilinear, it means first we perform linear interpolation on all the 4 points and two curves. So first we perform linear interpolation over A, B, C, D, and P1 and P2 curve, and we don't touch the remaining two curves, Q1 and Q2. And this is the final interpolated surface which we get, which is presented by S1UV. And when we do the same linear interpolation over Q1 and Q2 with all the 4 points, we get this surface S2UV. So these are the two resulting surface which we get, and these are the equations from which we can calculate these surfaces from the given curves and the points. So now, if you can see, this is the final equation which represents our bilinear Kuhn's patch. So it does contain S1 plus S2 minus S3. So it does contain extra one surface. Now, why the question arises here is, why do we do that? So what happens is, when we interpolate A, B, C, D, when we add these two surfaces together, S1 and S2, now adding these two doesn't interpolate A, B, C, D anymore. So what we do here is we introduce a new surface which is linear in u and v direction, and which is dependent on all these 4 points A, B, C, and D. and this is the equation for getting the S3 surface. And then we will add these two surfaces together and subtract this third one, and finally we get our bilinearly Kuhn's patch, and which is represented by this colorful diagram over here. So this is how it will look. Now for this surface there are some pros and cons. The advantage is that the bilinear curves are very easy to build, but the negative thing about it is that there is no precise control over the shape of the curve inside the patch. So that is the disadvantage of these kind of curves. And their applications are includes some special pattern design applications such as security printing and plain artist design. So that's all for the bilinear Kuhn surface. Now we'll move ahead to our bicubic blended Kuhn surface. So um, how do these surfaces come into existence? So if there are two bilinearly blended Kuhn's patches share a common boundary curve, so what happens is they only represent c raised to power 0 continuity across that boundary, which finally means that the combined surface will have a crease over the common boundary. And so to solve this problem, bicubically blended Kuhn surface were introduced by Mr. Kuhn, and the surface is used to used to produce very smooth curves. So at the point where these two surfaces share a common boundary, that will be smoothened out and there won't be any creases left. So that's why these surfaces were introduced. Now we want to so Kuhn's develop higher order patches using cross boundary derivative fields. So what we assume here is that Ck of u and Cl of v be four boundary curves which satisfy these two compatibility conditions over here, which are present by these two equations. And we will also assume dk of u and dl of v be the four boundary derivative fields, and these are the equations for those derivative fields. Now, when we want to construct a surface which has the ck of u and cl of v as its boundaries, and the dk of u and dl of v as its first partial derivative fields along the boundaries, then they need to fulfill two conditions. The first one has to be that the ck of u and dk of u Ck of u and dk of u will be compatible in B-spline sense, and similarly Cl of v and dl of v will also be compatible in B-spline sense. The second condition which needs to be fulfilled by these curves and the partial derivatives are that they need to fulfill these four compatibility equations which of twist vectors, which are present by Tk of L. And right here in this diagram, we can see that these four boundary are presenting our four input curves, which are denoted by Ck of u and Ck of v and all that. And these are which are these pointed arrows. All these are the partial derivatives along those curves. And at the tangents, we can see we have our twist vectors denoting. Now, this slide shows us the algorithm which can be used to produce the bicubically blended Kuhn's patch. So in this algorithm, we can see that CK, CL are the input arrays for the curves, and DK and TL represents the derivative field arrays. These all are four inputs, and all the remaining variables, they represent the output of Kuhn surface. Now, the first point is to calculate the control points of for surface 1, um, and these are the equations which can be used to calculate the control points for surface 1. Similarly, the second step is to compute the control points for S2, and these are the equations which can be used to calculate those control points. And then the third one is to calculate the control points for TUV, which is the tensor product surface, and this surface will have uh, 16 control points, and these will be calculated using these equations. So these are the first three steps in the algorithm. Then the second step is to calculate the degree of the CK and DK derivatives, CK curves and DK derivatives, and similarly CL and DL derivatives, which are presented by PCD and QCD. And when we once we found out the degrees, then we assign the maximum value between those degrees and between number 3 to the new two variables p and q. And then the two-step comes of the degree elevation and non-refinement, which were explained by my teammate Vamsi in the starting slides. What are these degree elevation and non-refinement? So we perform these two steps if required over these surfaces S1, S2, and T surface to PQ. And then when we if we do the degree elevation, we calculate the u naught vector of S1 and assign it to capital U. Similarly, we calculate v naught vector of S2 and we assign it to capital V. Then for doing the knot refinement, we calculate the number of u knots, and then minus and subtract the p variable from that, and then subtract 2 and assign it to n. And similarly, we do calculate the value of m. And the last step will be to calculate the control points of our actual resulting bicubically blended Coons patch, which can be calculated using this equation right here. So this equation can be used to calculate the control points and then plot our surface on a three-dimensional plane. So yeah, these are all the equations which can be used in the steps described in the algorithm. And this slide shows us here the control net, all the control points and the resulting surface from those control points for the surface, for the cubically blended surface in the u direction. And these diagrams at the bottom shows the control points and the resulting surface in the v direction. Yeah, so one thing to notice is that we find out the Bezier, the cubically blended surface in the u direction will be a Bezier surface in u direction, and it will be a B-spline surface in the v direction. Now, this is our slide. These diagrams here just represent the bicubic tensor product surface and its control points. And here I have mentioned that these three surfaces, S1, S2, and T, they must be made compatible using degree elevation and knot refinement techniques. And this is the equation to calculate our Coon surface's control points. So right here at the topmost part of the slide, we can see SU of V is the resulting bicubically blended Coons patch, which can be calculated from by adding these two and subtracting the tensor product surface. And these are the control points for our Coons surface. And this is the resulting Coons surface from those control points. And the most common use of these kind of patches is an attempt to fill a three or four-sided hole in a patchwork of surfaces smoothly. So that is the application of these surfaces, and that is all from my side for the Coon surface. And now my teammate Prashant will show us some design examples for all the surfaces which we have discussed so far. Thank you.
Hello everyone. So I'm gonna show some design examples. So here this is a half face. In this one, the author designed this half face using swung surfaces. So here the S-shaped curve, this is the profile curve, and the semicircle, this is the trajectory curve. So if we swing this profile curve along this trajectory curve, then we get this half face. So if we use full circle instead of the semicircle, then we can get the full face. So here this is another example. In this one, the author designed a pipe using skin method. See here the author used a lot of curves, I mean circles, so he can align them in the shape of the pipe. By using this skin method, we can get this pipe by using the circles. So in order to get these shapes, first we need to design this cross section like this and T-shape this square and eye, and then we need to sweep the surface along a straight line to get the surfaces. And for GMLab, we designed a cup, and we are gonna display how we designed it in Blender. So this is the cup that we designed. See, so in order to design this curve, just give me a second. This one, this S-shaped curve, this is the profile curve, and if you see this here, you can see a circle, and this circle is our trajectory curve. So if we swung this curve along this trajectory curve, then we get the cup shape. I will show you how. See, like this, we can get the cup shape by using swung surfaces. So now if we change the shape of this curve, then the shape of the cup will be changed. See, like this. Thank you very much.